Yeah, okay. So I'll continue working on the background. So if I were to start. Now, this is the minimal description of a quantum system. You have a bunch of states, um, and you operate on states by applying unitary operators to the states. And that's all good fun. But if you want to actually get some information, then at some point you take a measurement, and then you get some classical output. And so in the last lecture, we talked a bit about the unitary operators, in particular the exponential of IT, exponential of IH. So that's our unitary operators. But clearly the states are important, okay, and as are the measurements. And so I'll be talking about that today. Now, the underlying mathematics for this is the theory of quasi-semi-definite matrices. So we're talking about that largely. Now, my definition of a state is that it's a density matrix. And so what's a density matrix? Well, it's a few steps to it. The first step is it's a quasi-semi-definite matrix. And the second step has got trace one. So let's go through this slowly. So a quasi-semi-definite matrix is a mission. And it's got the property that for any vector u start mu is non-negative. Now, if in addition you have that u start mu is 0, implies u is equal to 0, then m is said to be positive definite. Now, a warning about terminology, the physicists use the word positive in place of positive semi-definite. And so I'm not quite sure what they do when they have a positive definite matrix or when they have a real matrix whose entries are positive. But so a physicist, when they talk about a positive matrix, will normally mean positive semi-definite. Now, I'm going to use the curly brackets there. The curly brackets there to indicate that this is to indicate that the difference of M and N is positive semi-definite. Now, positive definite matrices are very useful in practice. Well, they underlie a lot of quantum computing, and they're also very important in optimization problems. But since in our linear algebra courses we don't teach anything that's less than 100 years old, you don't see them discussed in the undergraduate courses as a rule. If a matrix is positive semi-definite, we write the strict curly greater than or equals in place of the greater than or equal, just this one. So we won't have much occasion to deal with positive definite matrices. And so generally, this is what you'll see. Now, the important thing is the examples. Well, the simplest example is the identity matrix, which is certainly a mission. And certainly satisfies x start x is non-negative for all x. And in fact, in that case, if x start x is 0, then x is equal to 0. So the identity is positive definite. Now, the next example is simply just to take a non-zero vector z and look at z star. This is now a rank 1 vector, a rank 1 matrix, square matrix m by n. And you can go back to the definition of positive semi-definite. If you take x transpose times z star times x star, the result's just the square of x star z. And so it's non-negative. Another simple observation is that if m and n are positive semi-definite, then their sum is. You prove this just by applying x star on the left and x on the right, and so then that divides into two terms, each of which is non-negative. And the fourth class I want to mention here is any projection. Now, there's more than one way of proving this, and actually this is one of the features dealing with positive semi-definite matrices. There's usually at least 3 interesting ways of proving any particular fact. One way of seeing it is a projection, is the way I've set it up, is a sum of rank 1 matrix, is a sum of matrices that form z star. Okay, and since each of those z's, and so when you take the x transpose projection x, you're taking x transpose x star x z star x, and so you get that the sum is that sum is not negative, and so projections are positive semi-definite. We'll work out a little bit of theory in a minute. There'll be some other proofs that we can see, other ways we can see it. There's at least 3 or 4 useful definitions. It's something unusual. Often you have more than one definition of a term, but usually only one of them is useful. But in this case, you really have 3 or 4. And the first one is simply the requirement that x star x be non-negative. And now there are a bunch of others which we're going to get to now. So for that, I need something. If I've got two matrices in the same order, then the product A times B starred is equal to that sum of outer products of vectors. Now, normally when you can multiply two matrices, you take a row of A and a column of B star, and so you take the dot product, so you're taking inner products. And so you're viewing the, so the product of A, B star would be a matrix whose entries are inner products. But you can also use outer products. And this is useful from time to time. It's a bit surprising the first few times you see it. But so A, B star is equal to that expression shown there. Now, it's much better if you work it out. And even if you just work it out on a 2x2 example, I'm not sure we'll make an exercise, but just so you can prove this. And so we can write any product. Well, that's a sum of rank 1 matrices as it happens. Now, the important point there is that A starred will be a sum of things that form AI starred, and each of those is posi-semi-definite, and the sums of posi-semi-definite are posi-semi-definite, and so AA starred is non-negative, is posi-semi-definite. Now, if you have a projection, let's call it E, then E starred is equal to E, and so that tells you that E starred is posi-semi-definite. Sorry, E squared is posi-semi-definite, but E squared is equal to E, so E is posi-semi-definite. So that's a second proof. Okay. Now, so having given a short list of the properties of posi-semi-definite matrices, a density matrix is a posi-semi-definite matrix with trace 1. And the simplest examples are the rank 1 symmetric or the Hermitian rank 1 matrices. And the it's worth noting if you have a Hermitian rank 1 matrix, so you've got a matrix ZZ starred where the norm is Z is equal to 1, then that matrix represents a orthogonal projection onto a one-dimensional subspace spanned by Z. Now, the important thing is in linearity, you say, oh, you're given a subspace, but there's at least two ways of being given a subspace in practice. One is you may be given a bunch of vectors that span it, or if the person you're dealing with is being kind, they might give you a basis. But so you're given a spanning set of vectors, and with that, you can generate vectors in the subspace. The other way of doing it is to give it, well, there's probably three ways. So you can also describe the subspace as the kernel of some matrix. Okay, and but from our point of view, what I want to do is I say that if I have a one-dimensional subspace, I can give it to you by giving you a non-zero vector in that subspace, probably a univector, or I can give you the projection onto the subspace. Now, the projection determines the subspace, and it's often more useful when the point about the projection is you can test whether something's in the subspace or not. If I'm projection is very useful, and so you have two different flavors. You can take the one-dimensional subspace or the projection. Now, the physicists will be normally thinking of the one-dimensional subspace, and since they don't really want to work with the subspace, they'll say, well, pick a unit vector on that subspace. But don't forget, we're dealing with complex matrices, and so you can multiply your unit vector by any complex scalar of norm 1. So you have a bunch of different vectors you can use. And now the issue here is when you ask a physicist what a state is, they're likely to tell you that it's a unit vector in a Hilbert space, in a complex inner product space. Now, that's wrong as stated because it's at best an equivalence class of unit vectors. Okay, so you can take the unit vector and multiply it by any scale of norm 1. So you have a bunch of unit vectors, and any one of those vectors will determine the same state. Okay, so you've got a choice. Now, a lot of the time it doesn't matter much, and so you just pick one and work with it. But the point still is there is a choice. And so my point is you can't really say that the unit vector is the state. It's really the one-dimensional subspace that it spans. The difficulty with that is at that point, once you say I'm dealing with one-dimensional subspaces, you're doing projective geometry. They don't teach projective geometry to physicists as a rule, so they don't want to do that. But still, there are two choices. You can use a spanning set or you can use a projection. And we're by and large taking choice we'll choose a projection. In any case, my definition of a state is that it's a density matrix. Okay, now there's a bit of a question as to what the state space is. And in a certain sense, you're better off not thinking about it if you just accept that the states are density matrices and they transform according to rules, which I'll show you in a minute. So any questions at this point? No. Yeah, okay, so but the short summary here is that density matrices, states are density matrices, and the physicists and the computer scientists would normally be working with what they call pure states, which are rank 1 density matrices. Okay, now in quantum computing, they often need to use density matrices that aren't pure states. It's less common outside that. So if you pick up the standard textbooks on quantum mechanics for mathematicians, they may not mention density matrices because they're all looking at points on the line and not worried about the finite dimensional case. I have one book on the quantum physics of mathematicians that says the finite dimensional case is too impoverished to be of interest. But that's another story. So a couple of short comments about positive indefinite matrices again. If a matrix is positive definite, it is invertible. This is sometimes a good way of showing a matrix is invertible, but we won't need that, so I'm not going to go into it there. And I'm very stating the fact here that, and if M is positive semi-definite and N is positive definite, the sum is positive definite. That's a fun little exercise. We won't be working with positive definite matrices much, so we'll leave that. What is important is that clearly the sum of two positive semi-definite matrices is positive semi-definite. And if you multiply a positive semi-definite matrix by a non-negative scalar, then that product is positive semi-definite. So any non-negative linear combination of positive semi-definite matrices is positive semi-definite. Now, if you want to work with density matrices, you can't take any linear combination. You need to take a convex linear combination. You want the coefficients to be non-negative and sum to 1. And then that way that linear combination will still have trace 1. And so it's important and useful fact that any density matrix is a convex combination of pure states. It's the first statement here. This statement is essentially trivial because it's just saying what I just said: a real number times positive semi-definite is a non-negative real number times positive semi-definite is positive semi-definite, and sums are positive semi-definite. But this is saying that every positive semi-definite matrix is a sum of positive semi-definite matrices of rank 1, and that any density matrix is a convex combination of pure states. Now, the physicists will sometimes say this means that density matrices are mixtures of pure states. It's not a very useful statement, and I've seen physics textbook, at least one physics textbook, which holds forth on this point. It doesn't really help to think of them as mixtures. There may be circumstances where it does make some sense, but in general, it doesn't. The other thing that's quite important is you can write the density matrix as a convex combination of pure states, but in general, you can do it in many different ways. Okay, so there's a vast number of ways of doing it, and so there's no right way of decomposing it. On the other hand, it can be useful to say that every density matrix is a combination of pure states, and these results sometimes let you transform questions about positive semi-definite matrices to questions about positive semi-definite matrices of rank 1, and that can make your life easier. Now, I want to summarize some characterizations of positive semi-definite matrices because there are 3 here. The first is the definition. I'll allude to this. This follows from earlier stuff that if M can be written in this factored form, N starred, it's positive semi-definite. And the third one is that all eigenvalues of M are non-negative. So this third condition here is both these conditions are important. And so together with we've got the 3 of them there, the definition, this factorization, and the fact the eigenvalues are non-negative. There's 1 or 2 more to come, but they're certainly important properties. And so if you're trying to prove things about positive semi-definite matrices, you've always got at least these 3 choices of going through it. Now, the third one is just saying that M is a sum of rank 1 matrices. We've seen that before. The last one is actually quite important. It says if N is positive, so the matrix M is quasi-semi-definite if for any matrix, quasi-semi-definite matrix N, the inner product M comma N is non-negative. Now, this is the sort of thing you can also what, but this is very important in optimization. The quasi-semi-definite matrices form a convex cone, and this is telling you that this convex cone is self-dual. Now, you can forget about that, but this is a very useful property of quasi-semi-definite matrices. And so one way to prove it is to notice enough to prove it for the rank 1 quasi-semi-definite matrices, since a general quasi-semi-definite matrix is just a sum of the rank 1s. So you only need to prove this for the rank 1 matrices. And if you actually try it, you'll discover that's very easy. So this turns out to be useful. Okay, and so I would say now you have really 4 effective ways of characterizing quasi-semi-definite matrices: the definition, the factorization, the eigenvalues non-negative, and the this fact about the convex cone. It's a non-negative inner products. So if you have a non-negative inner product with every quasi-semi-definite matrix, you're quasi-semi-definite. Now, because the eigenvalues are non-negative for a quasi-semi-definite matrix, it follows that the determinant of a non-negative of a quasi-semi-definite matrix is always non-negative. And it is also true that any principal submatrix of a quasi-semi-definite matrix is quasi-semi-definite. So do I want to make you do that? Maybe I do. Actually, that would be a good exercise, I think. The one important consequence of this is that the diagonal entries of a quasi-definite matrix are non-negative, because the diagonal entries are 1 by 1 principal minors. And so now, how do you get the diagonal entries of M? Well, you take EI star, or take a standard basis vector EI and take EI transpose M EI. Okay, so that's the II entry of M. Now that's non-negative because M is quasi-semi-definite, and it's the II entry of M. So there's the proof for the diagonal entries. And if you work with that a bit, you can write down a proof for the general case. Now, it's kind of interesting. For the 2 by 2 density matrices, there's a nice description. You can write every 2 by 2 density matrix in this form. So here you have 3 real parameters, A, B, and C. Now you can see that the trace to this matrix is 1. Okay, and the determinant is a quarter minus A squared minus B squared minus C squared. So the determinant is non-negative if A squared plus B squared plus C squared is less than a quarter. So the matrices D of this form that have non-negative determinant correspond to the points A, B, C inside the sphere of radius 1/2. Okay, and you can prove that on conversely any matrix of this form is quasi-semi-definite. You can one way to do it is to work out the eigenvalues, and so you have this characterization of the 2 by 2 density matrices. The physicists are very fond of this, and they call this sphere, or they rescale it so it's got radius 1, and then they call that the block sphere, which is just giving the three-dimensional ball a new name. It's not quite clear why that's necessary, but so you can. There's a nice concrete form for 2-dimensional density matrices. Okay. Now, if B and C are 0, then you're looking at diagonal matrices, and diagonal density matrices correspond to classical states. There's nothing quantum about a diagonal density matrix. Like that. The other comment which follows from the things I said earlier, that if, well, as I said, if M is positively definite, its diagonal entries are non-negative, and if the diagonal is 0, then M itself is 0. Now, well, one argument here is to say if it's positively definite, then its eigenvalues are non-negative. And the sum of the eigenvalues is the trace. So if the diagonal is 0, the eigenvalues are all 0. And the only symmetric matrices with all eigenvalues, or the only emission matrices with all eigenvalues 0 are the 0 matrix. Now, as I said, there's probably at least two other proofs of that. You can find different proofs because you've got all these different characterizations. And another fact which you can also prove using the eigenvalue is that if M is non-negative, then it has a unique positive semi-definite. If M is positive semi-definite, then there's a unique positive semi-definite matrix N such that M is equal to N squared. Now, the trick to this is to say, well, M is similar to a diagonal matrix with real diagonal entries and non-negative real diagonal entries. So that matrix has a unique square root there's a unique diagonal matrix with non-negative entries whose square is equal to that. And so you get from that, you deduce that it's a square. This can be useful on occasion. So we have a bunch of characterizations of positive indefinite matrices. So it's important to realize that you do have, well, I would say 4 characterizations. And it's often if you're stuck on proving something using one characterization, try another. You can nearly always find one. One of the nice things about positive semi-definite matrices is there's nothing really that's particularly difficult to prove. I mean, once you may have to take a while to see the right route to take, but generally speaking, the proofs are straightforward. So in that sense, it's a nice topic, and it's things are straightforward. Now, and this is summarizing again what I said earlier, that a quantum state is a density matrix. Okay. Now, if the density matrix is d by d, then the system has got dimension d. So there's a related Hilbert space, namely the d-dimensional c to the d. Usually the physicists are not working with finite dimensional things. They're thinking about particles on the real line, and then things are infinite dimensional. And so the basic assumption normally is that it's a separable Hilbert space, which I'm not going to worry about it because our Hilbert spaces will be finite, and so that condition will hold. And as I said, they will say that a state is a unit vector, which is technically wrong, mathematically a bit confusing. Now, the important thing is, as my diagram at the start, I had the set of states, and I said we could operate them on them with unitary operators. So how does this work? And the rule is quite simple. If you got a state D and a unitary operator U, then the state you get when you apply U to D is U D U inverse. Now U is unitary, and so U D U inverse and D are similar, unitarily similar, and so they have the same trace. So U D U inverse has trace 1, and they have the same eigenvalues. So U D U inverse is positive semi-definite. So it maps density matrices to density matrices. Okay, and here I've just worked out more explicitly in the case of pure states. So in that case, UD inverse is equal to this outer product. And so what that means in practice, if you have a pure state spanned by a vector Z, then you can regard the operation as mapping Z to UZ. And this is the way physicists would work with these things in their undergraduate courses. So they're not, as I said, they're not normally bothering with density matrices. I prefer to work with density matrices for a number of reasons. The most pressing one is that it generally seems to make the proof simpler. Otherwise, you start fudging. Yeah, I'm going to leave it at that. So again, any questions? No. I want to actually do some graph theory now for a while. I'm going to be talking about a topic which will come back when we talk about quantum homomorphisms and isomorphisms later in the course. So there's a connection to this. And this is also an example of how positive semi-definiteness can be used in practice. And so, and this is a algebraic graph theory in the title, so we should do some graph theory from time to time. So I almost invariably use A for the adjacency matrix of graphs. And so that means that A is real and symmetric. And so it's got a spectral decomposition. Now, in this context, I usually run my eigenvalues from index 0 through D, with theta 0 being the largest. So this is a normal assumption. So whenever I'm dealing with eigenvalues of graphs, I'm likely to start counting from 0, with theta 0 being the largest eigenvalue. Now, since the trace of the adjacency matrix is 0, because no vertex is adjacent to itself, and you don't want to forget this. So no vertex adjacent to itself, so the trace is 0, so the sum of the eigenvalues is 0. So that implies either that the largest eigenvalue is positive and the least eigenvalue is negative, or they're all zero. If they're all zero, you've got a symmetric matrix with all eigenvalues zero, and so it's the zero matrix. Okay, and so since generally we don't have any interesting questions about the zero matrix or the empty graph, we'll be in a position where we're assuming the largest eigenvalue is positive and the least eigenvalue is negative. Okay, okay, now the eigenvalues are only useful if they're related to properties of the graph. You've got to be a little careful here. I mean, the choice of adjacency matrix, you take an n by n matrix, rows and columns indexed by the vertex of the graph, and you put in a 1 in the ij position if vertices I and j are adjacent. But that choice is a little arbitrarily. I mean, why are we using 1 and not -1? And if you do that, well, you change the matrix, you change the eigenvalues. And so or you could add 1 to to each entry in the diagonal, then the eigenvalues will increase by 1. So and as I said, there isn't really a canonical choice of adjacency matrix. Certainly the one we use is convenient and obvious, and that's what we'll continue to use. But my point is, if you change the scaling, then the eigenvalues change. And so you discover that the formulas we see for eigenvalues often involve differences in ratios. And one of the reasons for this is that the differences take care of actual shifts of the matrices, and the ratios take care of any scaling. But anyway, having said that little statement, let's go on. If a maximum valency for the vertex of a graph is k, then the largest eigenvalue is less than or equal to k. Now, something stronger is true if equality holds and the graph's connected as regular, but I'll leave that for you to think about. Now, the next comment is I'm going to be dealing about, so I've got an adjacency matrix. I'm going to take a vector z indexed by the vertices of the graph, and I'm going to compute a times z. Now, it's fairly important to bear in mind that the eigenvector is actually better to think of it as an eigenvector, or even this vector z here, is best thought of as a function on the vertices of the graph. It'll take a while to convince you of this, but there's two reasons for doing it. One is because in the end it makes your life simpler, and the second is the viewpoint I take all along. So I'm always doing eigenvectors and all these vectors z as functions on the vertices of the graph. Now, we're interested in eigenvectors, so we're going to assume that we've got az equal to theta 0z. That's the eigenvector corresponding to largest eigenvalue, theta 0. Now, this equation can be written in the following form, that if I pick an index r, theta 0 applied to zr is the sum of the z sub I, where I runs over the neighbors of r. So the idea is we've got a function on the graph which takes value z sub r on the r third x, and it's being replaced by a function which, if you apply a to that function, you get a function whose value on r is the sum of the value's original function on the neighbors of r. So to get the entries of AF, you're summing the values of the neighbors of the entries summing the values of the neighbors of F. Okay, and so that gives us this formula, and this is in a sense much more useful than this formula. And now in this case, all we do is we take absolute values of both sides, and theta 0 is positive, as I said before, and so we get this equation. Now, this is true for any r. So then that's first comment. Second comment is the number of terms this sum is at most k, because we're summing over the neighbors of r, and the maximum valency of vertex in the graph is k. So there are most k terms in the sum. And so we're free to choose r. So let's choose r so that the absolute value of zr is as large as possible. So this is the largest entry in absolute value. Okay. Then each of these guys is less than or equal to zr, and so by straightforward calculation we get this. Okay. So here we have this is less, or the observation is the right hand side is less than k times the absolute value of z sub r, and that gives it theta naught is less than k. Now, whenever you derive an inequality of any interest, you're obliged by union rules to always work out what happens in the case of equality. I haven't done that here. If you do it, you would discover that well, if you assume the graph's connected and equality holds, then the graph must be regular. But we won't be needing that. So I just want the fact that if well, it's worth observing that the largest eigenvalue is a lower bound on the valency, and if equality holds, although I don't need it, then the graph is regular. So there is a connection, but this is the first connection between eigenvalues and properties of the graph. Now, the couple of other things we can do, if the graph is regular, then the all-1 vector is an eigenvector, because when you apply A to it, if the graph is K regular, then A times the all-1 vector is just the vector of with all entries equal to K. And it's only slightly more difficult to see that the converse is true, that if the all-1 vector is an eigenvector for the graph, then the graph is regular. Okay, so we have that. And the other thing, which again I'm not going to bother to prove, if the graph is K regular, then K is an eigenvalue of A with multiplicity equal to the number of components of the graph, the number of connected components. Okay, so that's so there's that connection. Now, there's a bit more theory I need before I get to the bounds I want. So I'm starting with the graph on n vertices. And there are three equivalent statements: that the graph is connected and regular, that the all-1 vector is a polynomial in A. I proved this, I think I did, and that the spectral idempotent belonging to theta 0 is just 1 on n times j. Now, the one way of saying, if the graph's connected and regular, then it's got the largest eigenvalue is K, and that's simple by the stuff I just showed. So that means that the spectral idempotent corresponding to theta 0 is just z starred, where z is a unit vector spanning the eigenspace. Okay, well, the only unit vector spanning the eigenspace to play with is 1 over the square root of n times your 1 vector. And so that tells you then that if the graph's connected and regular, then E0 is equal to 1 on n times j. And we know that the spectral idempotent are polynomials in A, so we get this. Now, if j is a polynomial in A, it commutes with A, and that we go back, follows from this statement that the graph is connected and regular. So this is reasonably straight. If you have spectral decomposition in hand, and use it as I just did, then this is reasonably straightforward. This polynomial is often referred to as the Hoffman polynomial of the graph, okay, because he was the first to make use of this. And as I'm saying, well, it's a useful observation, and really it's an easy consequence of the fact that the connected K regular graph, the all-1 vector is an eigenvector. The eigenvalue is K, and K is simple, and the spectral decomposition. Okay, so we have some bit of theory there. So we'll leave that for now and go on to the bound I want to talk about. So a co-clique in a graph is a set of vertices such that no two vertices in set are adjacent. They're sometimes called independent sets or stable sets. Independent might be slightly more common. I think stable is a bit out of fashion. And the maximum size of a co-clique is denoted by alpha of x. Now, there might be disagreement about whether it's a co-clique or an independent set or a stable set, but the maximum size of a co-clique is always alpha of x. So the theorem I want, now I should say before I go on that, co-cliques, well, I'm interested in mathematically, there are a lot of sort of combinatorial optimization problems where information about the maximum size of co-cliques will be relevant and useful. So it's very nice to have good ways of computing the maximum size of a co-clique in a graph. Now, the bad news is that it's an NP hard problem. Okay, it's equivalent difficult to the problem finding the chromatic number of a graph. So it's not easy to determine the largest co-clique, but it is an important problem in practice. And okay, so that's by way of background. The theorem I want, let's do it this way, is if I have a K regular graph with least eigenvalue tau, but it's not tau sub 1, tau comma, then alpha of x, the maximum size of co-clique, is given by number of vertices divided by 1 minus k on tau. So this is an explicit upper bound on the size of a co-clique. Now, the thing to bear in mind here is that we can compute, well, leaving out a few weasel words, we can compute the eigenvalues of a graph in polynomial time. So well, we need to specify the accuracy, but alpha of x is an integer, so we don't need anything too wonderful. So we can compute the right-hand side in polynomial time. Now the parameter on the left-hand side is, as I said, NP hard to compute. So it's not, in most cases, this bound is not going to be tight, but it is tight in many interesting cases. And so a little bit more about what's going on. The point is, if you have a co-clique, you can write down a characteristic vector with 1 on the vertices. So it's the function that's 1 on the vertices in the co-clique and 0 on the rest. And if it has size equal to this, then the characteristic vector shifted is an eigenvector for x with eigenvalue tau. So if equality holds, you actually have an eigenvector with a known eigenvalue. So it's a known eigenvector with entries 1 and 0, and then this constant, small constant, size of s on v subtracted from each entry. So it's a vector with 2 distinct entries. Okay, in fact, 1 minus the size of s on v, or minus the size of s on v. So it's 2 entries. It's an eigenvector, and its eigenvalue is tau. Now, that can be used to do things like prove the Erdős-Korona theorem, but we won't be doing that. But I just want to make the point: you do get some information in the case of equality. And as I said, you should always ask that question. But the question we're concerned about now is this bound. Now, I will say later on in the course, when we get to the quantum version of some of this, we'll have quantum co-cliques, but it turns out that the same bound holds. And so, which is a very surprising fact. But anyway, so we're just doing the classical version now.
Chris,
yes?
Excuse me. Can I ask
Yes?
a question about this?
Of course.
So earlier you said that we can think of an eigenvector as a function on the vertices of the graph. Then so are you thinking about a vector of vertex label as the domain and some real number as the image? Like what is mapped from what to what?
Okay, I get very nervous when people start talking about labels on their vertices, as some of the people here will realize. So my graph has got a set of vertices and a set of edges, and edges are pairs of vertices. Now, I've got a set of vertices. Now, normally we just use numbers 0 through n minus 1 or 1 through n. So that's my set. Okay, and so I have a fixed set of vertices. I usually use v for that. Okay, and so when I say I've got functions from v to the reals or the complex numbers, depending on what I'm doing. In this case, it's the reals. Okay, so I have a function. Sorry, go on.
Are we thinking about any combination of the vertices, or like how do you decide?
I mean, when you write down if I have a graph with n vertices, I write down an eigenvector. I write down a vector of length n. Okay, and I have n real numbers, one over the other. So what I've done there is describe a function which maps the ith vertex to the entry to the ith entry in that column.
Oh, okay.
Okay, so yeah, I mean, you can. So the point is that we tend to write our vectors as, numbers one over the other. This is less effective when you're working in the vector space of complex matrices or continuous functions. But if you're working with R, E, N, or C, and yes, it's possible to write down your function. So in some sense, that's a very sort of an expanded way of specifying the function.
And when you mentioned,
sorry, let me just go on a bit. So what you're doing when you write down the vector like that is you're giving a table, and on one side you've got the inputs, on the other side you've got the values. Okay, and then you just think of the column giving the values as being your vector. What I'm saying is what you're really dealing with is a function, which assigns a real number v sub I to the ith vertex, or to the vertex I to be precise.
Right. Then when you mention eigenvalue, whose eigenvalue it is?
Well, it's an eigenvalue of the operator of the matrix.
And because how is it related to the vertex?
Well, the eigenvector is neither is directly related to the vertex. I would prefer to say that both the eigenvector and the eigenvalue are properties of the entire graph. I mean, the vertex in simplest case is just it's just an integer between 1 and n. I mean, it doesn't have any interesting properties, really. Now, this is an important question, so I don't want to I'm willing to spend quite a bit of time on it. So please keep coming back if there's something's not clear.
Okay, thank you.
The other thing is that something like this, what will happen is later on something else will come up related to this, or we'll ask again, because it does take a while. I mean, when I teach the algebraic graph theory course, when I used to, I mean, this is, it always causes difficulties because you're conditioned to think of the vectors in a certain way. And it's not always it's not always the easiest way to do it.
Okay, thanks.
I guess the other comment of the physicists is they're very concerned with doing a calculation and getting an answer out. And so when I make snarky remarks at what they're doing, but what they're trying to do is set things up so they can do a calculation and get a number out. Okay, whereas I'm a mathematician, I'm less concerned with doing that calculation at this point. I'm thinking more about what's going on. And so I'm doing something different from what they're doing. The physicists want to get a number out. I want to think a little bit more about what the underlying mathematics is doing, but they don't really want to do mathematics. They just want to get the answer. Okay. Any other questions?
Chris,
Yeah.
Just to be clear, so when you say eigenvalues, you're talking about eigenvalues of the adjacency matrix, right?
Yes, I was talking about, yes. And of course, I don't know if I've done it already, but I was also talking about eigenvalues of the graph. But the eigenvalues of the graph are eigenvalues of the adjacency matrix.
Okay, thank you.
So there's nothing, I'm using the same eigenvectors and eigenvalues that you used in your linear algebra courses. I'm just looking at them slightly different. So when I say an eigenvector, it will be you will be able to write down there will be a matrix A and a vector Z, and A times Z will be lambda times Z. So I can always translate that back to that if I wanted to. But as I said, in many cases, it doesn't apply so much to what we're doing here, but in many cases, it's much more useful to think in terms of the functions on the vertices. And then my adjacency matrix becomes an adjacency operator because it's mapping functions to functions. Now, of course, we don't do this undergraduate course because students don't like would like to think of functions as vectors, but I mean, they are. Okay. So let me look at the proof on. Actually, I think I can do the proof and we'll stop. So I'm assuming I want to prove the bound hold. I'm not going to worry about the eigenvector stuff. So I'm going to take a subset of the vertices with covariance vector X, and this is going to be a co-clique. Now, the first thing to notice is that when you compute X transpose X, it's the number of pairs of vertices UV in S times S to where U and V are adjacent. Okay, so X is a 0, 1 vector and X transpose 0, 1 vector. And so basically you're summing the entries in a block of A. You look at the entries of A that are indexed by elements of S. Okay, so you get a square block of A, and X transpose AX is the sum of the entries in that block. Okay, so and so in other words, that we discover that S is a co-clique if and only if X transpose AX is equal to 0 for X, the characteristic vector of S. Okay, so that's comment number one. So that's how we're going to go backwards and forwards between So we're talking about co-cliques, which is a combinatorial thing. We want to work with linear algebra and vectors, and so we have to replace the co-clique by a vector, and we need to recognize when the vector is actually going to give us a co-clique. So X is a 0, 1 vector, and it satisfies this condition. And so now I pull a rabbit out of a hat. I'm going to take this matrix. It's the adjacency matrix. There should be an I here. We subtract tau times I first. Now, the eigenvalues of A are theta 1 through theta D, where theta D is tau. So if we subtract tau from each of those eigenvalues, we get a non-negative number. So the point is that A minus tau I is positive semi-definite. Okay, now, as I said, I think that should be a J. It's a nuisance. Yeah, there should be a J here. So what we're doing is we're subtracting K minus tau times the idempotent E0 from A. Now, A is theta 0 times E0 plus some stuff. And what we're doing here is we're subtracting that first term from the sum, throwing it away. Okay, and so the point is this is a positive indefinite matrix. Okay, and it's this part is we need to make the proof work. The fact that if tau's least eigenvalue and A is symmetric, then A minus tau is positive indefinite is more straightforward. Okay, so I've done that. So B is positive indefinite, and so X transpose BX is greater than 0. And so now we just do the expansion. So X transpose BX is X transpose AX, and here's where the J should be. So we get this term corresponding to the second term, and we get this, so we have 3 terms. Now the first term is 0, because we're dealing with a Coke-League. The second term, well, X is a vector of 1s, and J is a matrix full of 1s, and so this is just equal to the size of S squared over V. And finally, X transpose X, that's equal to the size of S, so we get this sum being non-negative. So you get all this is negative, and when you unpack that, you get the bound that S is less than V over 1 minus K on tau. Okay, so the point is you write down that we're using a couple of things. We're using the fact that we can recognize Coke-Leagues by this condition, and we're using the things we can form this positive indefinite matrix, and then we do this. And so there's the proof. And so we have a bound on the size of Coke-Leagues. Now, yeah, and so I won't say any more now. I went over, and this is exactly when I should stop. So that's the end of it for today. Lecture.